Okay. I think I'm ready to start. Oh, except I have no pen. First thing I want to do, I need this today. First thing I want to do is update you with some exam news. First of all, we know that we're grossly behind on grading, and we are really, I swear to God, we're working on it. The other thing I want to announce is some news on Exam 7. Okay, so here's the deal. We are going to have Exam 7 be a retake of any exam that you like. Okay, so you will show up to the testing center and you can retake your, say, worst exam. And if you score better, we haven't figured out what to do if you score worse yet. This is all just, we're figuring it out. But if you score better, it will replace your original score and serve as your Exam 7 score in your, in your average. So we feel like this is our way of satisfying everybody, right? Like you can improve one of the exams on which you choked. That never happens. And at the same time, you have to work a little bit to do it. We're not just going to drop an exam. Sorry. So that's the story. Yes? Oh, good question. Will it be the exact exam or will it be a randomized version of that exam? It'll be a randomized version of that exam. So it's the same topic, but a different exam. Yeah? Yeah, that is our solemn promise that you will know what your exam scores are by the time you have to make that decision. Okay? Let's see, what else? Any other questions about that policy? Like I said, this just occurred to us this morning. We're like, what are we going to do about these exams? And this was our solution. So I'll send out a clarification of the policy and an official statement of that policy, and it will include what happens if you do worse. Oh, yeah?
So the exam retake will count in Exam 7?
Yes, it will count. So yes. So the question is, it will also count as Exam 7, and the answer is yes. So you'll get twice the points. You know what my intention is, what I really want to have happen, I want 700, 100%. Okay, I want everybody to get an 100% on it. Yeah? Can you say it louder, please? Yeah, I don't know yet. Like I said, the whole thing isn't spelled out. Like, what if you don't want to retake an exam at all? Okay, I don't know yet. Okay, we'll figure that out. Okay, and yeah. We won't have material. It has to be a reasonable answer. It has to be, oh, we'll give you your highest exam score for whatever Exam 7 would have been, right? Like, or something like that. Because we don't want to write another exam. See, everybody's happy. I'm telling you. Okay. So we were talking about hash tables. Okay? Now, there are 4 phrases that live together oftentimes, and they're oftentimes referring to kind of the same thing. Those 4 phrases are dictionary, hash table, associative array, and map. Okay? Now, those 4 phrases we throw around all the time, and we mean the following. For any one of them, we mean the following. Abstract data type dictionary implemented as a hash table, which is what we're going to talk about today, with an interface that is an associative array. Okay? And it behaves like a map in the mathematical sense. It behaves like a bijection. All right, so those four things, those four ideas, play a slightly different technical role in our description of the structures that we are using, but they're oftentimes interchanged in our conversation. So if we're talking about some big problem to solve, and I say, oh, just use a hash table, I probably mean use a dictionary whose interface looks like an associative array that's implemented with a hash table, okay? But I'm almost never, none of us, are hardly ever going to say that whole big clear description of what's going on, okay? So, again, the abstract data type that we're talking about, still, I'm a little tired of it, frankly. We've got some awesome data structures left, and I don't get to talk about them yet because we're still talking about dictionaries. So the abstract data type that we're talking about is dictionary. Our particular implementation is a hash table. The interface, okay, it looks like this. Now, thus associative array. So now, where are we exactly? Let me show you what I mean by that in terms of the way we write code in C++. We're providing the functionality for client code. So this is the stuff, say, that you might find in main or any other place that uses a type, which is a dictionary, and that allows you to do things like insert into it using these square brackets. That's the associative array part. And that allows for key value pairs that are of arbitrary type. So we're not going to specify ahead of time that the keys have to behave a certain way or look a certain way. Okay? Now, what we're going to discuss is the implementation behind class dictionary. So we're going to look at, okay, what's on the inside of this class that behaves in this way? Now, what's on the inside of a lot of classes is some memory that represents objects of that type together with some functionality. In this case, the functionality is the dictionary functions, and the memory associated with it and the way it behaves, the way that memory is maintained, is the hash table part, okay? So, what on earth does a hash table behave like? Well, it's something like this. My object, D, in this picture, D, gets a value K, and essentially gets a value K and a value V. Wait, a key K and a value V. And it needs to decide, how am I going to store this in perpetuity? Well, here's the strategy. There is a hash function, and I mean this both in the mathematical sense and probably in the programmatic sense as well, that takes as input the key K, computes h of k, outputs an index I, and in index I can't really write on that table because I don't know how to get my black pen. In that index I puts the key value pair in the array, in an array, okay? So the fundamental data structure for this thing that we're calling a hash table is simply an array indexed by small integer indices, just like all arrays that we've ever seen before. So what does a hash table have? It has for sure an array. And when I say that there, I mean nothing surprising about it. It's the same array that you learned about in week 2 of your introductory programming class. Okay? Any question about that? The other thing a hash table is guaranteed to have is a hash function. that takes an arbitrary key type as an object of an arbitrary key type as input and has as output some index. Okay? And we're going to actually spend the rest of today talking about these hash functions. And then the last thing it has is actually a mystery. I'm not going to tell you what that is now because you won't see the reason for it. I'm going to let you feel the reason for this last thing, and we'll talk about it after we see its motivation, okay? So this is like to be continued. This means you will come to class on Friday. This is my little insurance right here. Is that a joke? I don't know. I don't know if it's a joke. Okay, and then before we go on to the next slide, I want to remind you that Lecture Helper is available, lecturehelper.cs.illinois.edu. I would love it if you used it. It would be awesome. But if you don't feel like you need to, that's fine too. Okay, ask me a question. Fine. All right. So let's spend some time talking about these hash functions, okay? So don't read this blue yet. I didn't intend to write it there yet. So I want to create a hash function, a hash table, the whole thing. I want to create a hash table for key value pairs, which are the children in my neighborhood, okay, the names of the children in my neighborhood, and their Halloween costumes. Okay, that's my data. That's what my data looks like. Now, my objective is to be able to take the keys, which are the children in my neighborhood, and find a really good way of mapping those children into small integers so that I can store them in this table, store their Halloween costumes in this table. Okay? Now, I have a question for you before we actually do this, before we come up with this function. You can see the descriptions of their Halloween costumes. What I want to know is when you see the letters HP, what comes to mind first? Raise your hand if it's Harry Potter comes to mind first, and raise your hand if it's Hewlett-Packard. What is that? It's yet another thing that kind of differentiates us from the rest of the world. I don't know. Yeah, it's Harry Potter. The kids in my neighborhood are not that geeky. Okay. All right. Okay, so what I want now, so my whole objective is clear, I think. I want to store these. The children are keyed by their first name. And I'll tell you from the start that my hash function really only needs to work on this collection of children. There is not a kid named Isaac in my neighborhood. There is not a kid named Edward in my neighborhood. My hash function just needs to work on that set of children. So, can anybody come up with a reasonable hash function? Yes, what do you think? Yeah, very good. Here's what we're going to do. Our K into our hash function, our key K is the first name, right? I would put that kind of as a comment. And if I take K sub 0, which in a string is the first character of the string, minus capital A, I'm going to get a small integer between 0 and 7, and I can just store black cat here, HP here, etc., all the way down. Wasn't that cool? Or not? What it was perfect. That is, I have this fantastic ability to look at my set of keys and create a hash function that maps my set of keys into this table. Yay, I was lucky. Yes. Oh, yeah, this is a technical point that I always forget to say, so thank you very much. it's very typical to store the key and the value together just because it's hard to get the key back out after you hash it in. So for a matter of convenience, by matter of convenience, we probably either have another table where we keep the keys, or we store the key and the value together in the table. Does that clarify it completely? I will almost always forget to do that. Okay, just blanket what's the absolved. I'm absolved of responsibility because I admit it ahead of time. All right, any other questions about it? Is that okay? All right, so here's what I want you to think about. I want you to tell me what's special about our scenario here in this context that made this special hash function possible. And I don't want English, I want math. How would you describe what's special about this scenario mathematically? In general, when do we have the opportunity of creating these perfect hash functions? In general, when do we have the opportunity to create these perfect hash functions? The hash function is one-to-one. Very good. That is, there's no ambiguity. When you insert a key, there's a place for it to go, right? Oh, wait. And two things will not map to the same thing. We don't have to deal with Edward. We don't have to deal with Edward and his knight's costume, okay? There's only one thing, and that's one-to-one. All right, what else is nice about this one? It's also onto. That's right. That is, the implication here is that we're using our space efficiently, right? That, in fact, the elements of our key space map to our table in such a way that there are no gaps. They map to a sequence of integers that we can consider to be the indices of a table. Now, the reason I say it only a sequence of integers rather than a sequence of integers starting at 0 is you can always subtract, so that you can always subtract the starting value of the sequence and get to 0. Okay? So, a perfect hash function is a bijection. And a bijection, if there exists a bijection from your key space to a small sequence of integers, then we call it a perfect hash function. So this is AKA a bijection from the key space to a set of integers, a small set of integers. Sequential integers. I don't know what's going on with my pen. Okay? All right. That's an F right there. Small set of sequential integers. All right, any question about that? Yeah? Did you have a question? Or okay, I owe you coffee. Okay. All right. Just reminding myself. Okay. So I have a hash function for you. So this is a new scenario. I have a hash function for you, and I want to know how you feel about this hash function. Now, this demonstration has two parts to it. Part of it is the, is this a good hash function part? But the other part of it is, what the heck is the hash function? So this is a puzzle that was presented to me a few years ago by a student who was in high school at the time, but he was taking this class. And he said, I have a puzzle. You'll never figure it out. And I figured it out. It took a while. Don't get me wrong. I'm not like I'm so smart or anything. It took me a while, but I figured it out. And moreover, I promised him that it would appear in class someday later in the semester. Like he did this at the start of the semester, and I'm like, okay, this will appear in class someday. Now, the cool thing about this story is that his little brother was in the class last hour. So it's like this, you know, the whole family tree thing. And you know what? The really funny thing is his little brother, who's currently taking the class now, slept through the whole thing. It was awesome. Okay, I think you wouldn't mind if I told you that story. All right, so here's the scenario. What we're trying to hash are dice rolls of 5 dice. So this is already feels like a complex key, right? Like I do a roll for Yahtzee. I rolled it in my hand. Oh, look at that. Woo, cosmic. I got 1, 2, 3, 4, 5. That's a dice roll, right? I should be able to use dice rolls as keys. Like, for instance, I should be able to hash this key and store maybe a value of the dice roll or something like that. I'm going to compute a hash of the dice roll for you, and the puzzle is for you to figure out what is my hash function. What am I doing? Okay, so remember the hash function itself is what index would I store this dice roll in. So there's my dice roll. It's 2, 3, 5, 6, 6. And this dice roll, 2, 3, 5, 6, 6, hashes to value 6, hashes to index 6, sorry. So I would store, you know, the point value of that roll in 6. Okay? Any question about that? Okay. I'm going to do another one because despite what you're thinking, it is not the maximum value of the dice roll. Oh, that's the same. Was it the same roll? Oh. So this dice roll, 2, 3, 4, 5, 6, also maps to 6. Oh my gosh. It does. It maps to 6 as well. This is really, so this is 1, 2, 3, 5, 6, also maps to 6. Okay, come on, Cosmos. Give me something different. Phew. This one maps to 4. So 1, 3, 3, 4, 6 maps to 4. Okay, ready? I'm going to do it again. Should be sort of hypothesizing in your mind. This is called inductive learning. This one maps to 2. Okay, I'm going to tell you the name of this puzzle because the name of the puzzle ends up giving you a hint as to what the puzzle is. The name of the puzzle is Petals Around the Rose. Don't Google it. Don't Google it. That's not fair. So it also maps to 2. Boy, there's a lot of collisions in this. There's a lot of violation of one-to-one-edness in this hash function. This one maps to 4. Anybody want to hypothesize what this one maps to? Oh, brother.
5, 6, and 6.
What does it map to? 6 is correct. Oh. Maps to 8 is correct. Oh. Oh. Okay. We could do this all day. Oh, 10. Maps to 10. Anybody got it? Who wants to tell me? Yeah? Yeah, the rows. Pips. Yep. Right. So the name of the game is Petals Around the Rose. And the answer that I'm telling you is the number of pips that surround a central point. So the 4 and the 6 have no central point. And each of those, when you add all of those up, you get 10 pips around, each of which is around a rose. Okay? Any question about that? So there you go. There's your puzzle. All right, so do you like this hash function? Oh, brother. Come on, wake up. Wake up. Okay, we'll see where this throws us. Oh, brother. Fine. Okay, so did you like this hash function? So the hash function was petals around the rows. And it basically mapped these things to integers. So first of all, is my table big enough? Is my table big enough? Yes? Well, almost, right? The maximum value I could get is 20 here. So I should have made it 20 probably. All right, and there are a couple reasons why we don't like this hash function. How many different 5 dice rolls are there? Did anybody figure it out while we were 5 dice rolls? It isn't really 6 to the 5th because 1, 1, 2, 3, 4. 1, 1, 2, 3, 4 is not different than 1, 2, 3, 4, 1, right? Like you've got, the order of these things doesn't matter. 5, 4, 3, 2, 1, and 1, 2, 3, 4, 5 are the same dice roll, okay? So it isn't 6 to the 5th. But it is a lot. If you were in CS 173, you would call this a stars and bars problem. I think you do this there. You do combinatorics in 173, right? And we're not going to do it here, but suffice to say, the number is on the order of magnitude of hundreds. I don't think it's thousands. I think it's hundreds of different dice rolls, okay? And we have a function that maps those hundreds of dice rolls into this table, right? You can give me any dice roll, and I can tell you the value. So already, the fact that our key space is larger than our table, number one, it violates the one-to-one-edness, and it says already that we do not have the capacity, that our hash function is not going to be a perfect hash function because it violates the one-to-one-edness. Now, there's another problem as well. So this is not one-to-one. Is there another problem? Yeah? Yeah, right. Think about the dice for a second. None of them have an odd number around the outside, right? We're only ever adding up even numbers. So we will never use that or that or that or that, etc. We will never use the odd values in this table, which says, in fact, that, number one, the hash function isn't surjective or onto, but it also says we're not using our table efficiently. Now, that particular piece of this would be easy to fix. We could change petals around the rows to the puzzle petals around the rows divided by 2, right? And then we would have solved that problem. But still, it illustrates the fact that, this is just a bad hash function. Okay? Any question about that? Also not onto. No, not a good hash function. Okay. Here's the sad story. Oh, let's talk about hash functions. I need to back up for a second. Let's talk about hash functions. So here's what will happen. Hash functions typically will consist of 2 parts. They will first take your key, take a key of arbitrary type, and map it into an integer. And then there will be some compression algorithm that takes that integer and makes sure it fits in the particular array that you have described. So, in our context, and for every example we'll see in this class, the compression function is just mod n, table, where n is the table size. Okay, that's just kind of how we do it. So if we're creating a hash function, if we get a function that maps our key space to an integer, we go, okay, we're kind of home free, sort of, or at least partially home free. Okay, choosing a hash function is tricky. Lots of different things can go wrong, and I'll explain some things. I'll explain the broader context in which things can go wrong in just a second. And it's pretty, smart people have created bad hash functions. So I encourage you to look up, to do your history lesson for the day. And that is to look up Knuth's multiplicative hash. He expanded on it in The Art of Computer Programming, and it was actually posited as, oh, here's a really good hash function. And then it was discovered later that it didn't work. And I'll talk about a little bit why. What it means for it not to work in just a little bit. Okay, so what are characteristics of a good hash function? I'm pretty sure you would not like a hash function that did not compute its index in constant time. That is, if it took you time proportional to the size of your data to compute the index, you wouldn't be gaining anything over any of the other dictionaries that we're already using. Okay, so we demand that our hash functions be computed in constant time. They must also be deterministic. Now, what this means is if you see a key twice, so if you both want to insert and find on the same key, the same index must be produced by the hash function. Now think about what it would mean if there weren't, if that weren't true. It means that for a particular key, you're effectively saying, your data might be in index 10, or it might be in index 35. Good luck, right? So what we mean by saying it's deterministic is we're saying there is no randomness associated with the value of the index or the location in which it's stored. Formally, we can describe it as follows. If two keys are the same, if key 1 is equal to key 2, then their hash values must also be the same. Okay, that's it. And what we recognize is that, this might be two different instances of a key that has the same value. Okay, any question about it? Which one? What are you saying? Yeah, so the question is about, but wait a second, what if HK1 equals HK2? That is, what if your hash function maps two things to the same place? So I want to tell you all about this. Remember the question mark on the first page where I said, I'm not going to tell you about the third thing? This gets at the heart of the third thing. That is, how to handle the lack of one-to-onedness of your hash function is basically what we're asking. What do we do when two things map to the same place? We're going to argue in a minute that will definitely happen. Okay, that we can't avoid it. We can't always make a perfect hash function, and we're going to spend almost all of Friday talking about dealing with that exact situation. Okay? All right, let's see. Hash functions must also satisfy the simple uniform hashing assumption. And what that means is that your indices are equally likely to be spread out, or they're likely to be spread out uniformly over the possible indices of the array. Now, it means if you have a whole bunch of them, if you have a whole bunch of indices that you map, and you kind of take a look at how they've been mapped over the array, they're pretty much spread out. The way we describe this formally is for any index j not equal to k, for any key j not equal to k, the probability that h of j is the same, that is the probability that they map to the same thing, is proportional to the table size. That is, if they were selected independently, if these two values were independent, the probability that they would get mapped to the same thing anyway is like an n-sided dice roll, basically. Okay? Any question about that? Is it okay? The probabilistic argument is beyond the scope of the course because we're not allowed to assume that you have had a probability course. But I think this kind of is instinctive, right? Like, basically all it's saying is that the probability that any one thing falls in any one of the cells is proportional to the number of cells. That's all. Yeah? Table size. It's the size of your array. Thank you for making me be clear. And when I say table size, I mean array size. Sorry. Okay, I want to add a little bit of perspective to this because right now it feels like, at least to me, it feels like the search for a good hash function feels like the search for a bijection. And we're going to give up on that for general purpose hash tables for the following reason. Key spaces are big. If a key space is small, in general we say if the size of the key space is proportional to the table size, then we have hope of creating a bijection, right? Or at least some sort of nice mapping that might map a constant number of things to any one cell. Okay? So in this case, if our key space is small, then we would say that it's easy to create a table of all of our keys, is the way to think about it. Or it may be that in our table we'd have a couple different keys for each index. But we can do it just because there aren't that many. But that's not, and if your key space is small, like my neighborhood children, you should spend some effort seeking these nice mappings between your keys and the indices of an array. Totally worth it. It's totally worth it. But key spaces are almost never small, and especially in the case where we want general purpose hash tables where our keys can be of any type, we need the ability to, we still need the ability to make the hash table. Now, here's the discussion. Here's what's going on. So key spaces are big. That is, the mathematical descriptions of the things that your hash table might have to handle, ginormous. But what we're saying is that any sample size from that key space is not too big. We're going to take samples from maybe some huge key space and map them into a table. Okay, we're going to have space to store all our data. Okay, so the keys used might be like this. So here's what we want from our hash function. We want our hash function to take the sample from our key space and map them, pretty uniformly over the table. Moreover, if we would happen to get a different sample of, small sample of keys from our very large key space, we would want it to map kind of nicely over our table. Maybe a different way, because they're a different set of keys, but we would like them to be spread out over our table. But in future classes, you will argue more robustly that there are subsets from any reasonably sized key space. They don't even have to be all that big. There will be subsets that do not lend themselves to efficient mapping. That is, even if your hash function does well on several subsets, there are just so many subsets in a big key space of a particular size that some of the mappings will be bad for any hash function. As a result, we have to have a mechanism inside the hash table for dealing with these bad subsets. We deal with them using a collision resolution strategy. So these imply the need for, or they motivate the need for a collision resolution strategy, which is the subject of most of what we talk about next time. Okay? Any question about that? And this is, in general, how we handle any sort of non-one-to-one-edness of our hash function. Okay? All right, any questions about that? So anytime you have two things that map to the same spot, you have to have some strategy for dealing with it, because analytically, it will happen. It's impossible to create hash functions for big key spaces that are general. Yeah? We haven't gotten to it, but you can imagine n to be the very biggest array you can make. Okay? And even then, you're going to have problems. Even then, there will be a certain probability that two things will hash to the same place, and there are subsets where things will definitely, there's a pigeonhole principle argument that says two things will map to the same space, even if n is big, because n can't be big enough to handle all subsets of all key spaces without collisions. Okay? Yeah? So small is going to grow as you can have bigger arrays in your machine, right? So I want to rely on, a little bit on, oh, this is math, and ask you, and to also point out that it depends on the sizes of the other things you're trying to do in memory at the time, right? So it's going to depend a little bit on the magnitude of your keys and values. When you put them together, how much space do they take up? Basically, you are going to allocate a particular amount of space for computation. Part of that orchestrates an array. I don't know how big that is. It depends on what your keys and values are, how much each one of them takes up. You can go and try it out. You can just keep incrementing and building an array bigger and bigger, and you tell me how big of an array your machine will make, an array of integers, say. Okay? But it's that very specific question is related to the size of memory. And I just want to go, oh, it's getting bigger. Okay? All right, any other questions about this? All right. I don't know, it's probably 1 million for integers. I don't know. Depends what you're putting in your table. All right, any other questions about this? Okay, so an example of a key space for which we can develop a nice hash function are short strings. You don't like it when I use these fuzzy words, right? Short strings on the order of 8 characters. There exists a really easy hash function for 8-character strings into an array. And it involves simply interpreting the strings themselves alphanumerically. So doing an ASCII mapping from every string to its numerical value. Now you can figure out how big that is. Say there are 100 string or 100 characters for each of the 8 positions, and you can make an array that big. So okay, so for 8 character strings, we've got a good hash function, okay? If we had another half a day, we could spell out exactly what that hash function looks like, and you go, okay, I believe it, but we're not going to do that because 8 characters really isn't very long. What I would really like to do is to be able to take any 40-character string from a novel, say, and map it to the page number on which it appears for a given novel. Okay? And I was thinking about that application. I thought, oh, I know. I bet I can make a good hash function for 40-character strings, a good hash function for 40-character strings based on this 8-character string hash function, which is straightforward. So I thought about that. Here's the book that I was going to try it out on. This was my test book. And here's my hashing strategy. From any 40-character string, and by that I mean not necessarily the ones in the book, but just any 40-character string, I'm going to select 8 positions at random. Okay? And I'm going to instantiate hash function with those positions and use those as my hash value input into the 8-character string. So for example, here are a bunch of substrings from, I guess it's probably Huckleberry Finn, but it could be Tom Sawyer, I don't remember. I'm going to choose 8 positions here. Here, 1, 2, oh man, I'm not drawing straight lines. I'll try again. Okay, I'm choosing 8 positions. 1, 2, 3, 4, 5, 6, 7, 8. So do you kind of agree that I chose those at random? Do they look sort of randomly spaced? I tried to use a Poisson process in determining at what point I should. All right, and so now what I'm going to do is in each one of those strings, I'm going to look at the characters that are highlighted in yellow. Okay, I'm going to look at the characters in those positions. Okay, so I have O-R-E-E-N-I-N-I. Oh, that one's fun. And then I'm going to, for example, okay, do you see what I'm doing here? And this one looks like W-M space O space A-E-E. Okay, this one down here looks like N-E-T-I space Y-L space. Okay? All right, so now I don't know about you, but I'm looking at these things and I'm going, whoa. Those are random strings, right? There's no meaning whatsoever that I can deduce from these strings. So I'll bet you those are this thing that I have done, hashes, is a great hash function for 40-character strings, yeah? Like, I think if I spread those out over to, like, I computed the ASCII value of each of these, they're pretty spread out. No way those are going to be close. If I was worried about it, I could even jumble them up, right? If I wanted to. Okay? Do you agree? Does it look like it? Those feel like random strings, right? So I guess I can create a hash function for 40-character strings. I have a hash function for 40-character strings. Yes? Yeah? Sure. Okay? Okay. So let's take my magic hash function and apply it to these strings instead. What are these strings? Yeah, these are random URLs from Wikipedia. There are lots of Wikipedia pages, millions of Wikipedia pages, okay? And so it's sort of reasonable that I should be able to come, like, they should be spread out. It should be pretty easy to spread those out, to choose a random selection of those. But look, if I just made an awesome hash function for 40-character strings. So I should be able to apply it to any subset of 40 character strings. So let's do that here. Okay, here's a position 1, 2, 3, 4, 5, 6, 7, 8. Because 40 characters is really about there. So, all right, so what do I get for that? I get T colon N K D R I percent. And down here, when I look at it, I get T colon N K D R I H. And down here, when I look at it, I get T colon N K D R I little a. So how do you feel about how that hash function does on this particular subset of 40 character strings? Not good at all, right? It took all of those strings. In fact, it takes all of Wikipedia, the million pages of Wikipedia, and no matter what subset we draw from them, they're all going to hash to about 100 different places, or 26 or 50, whatever, you know, some small number of places. So it creates exactly this red blob here of a badly hashed subset. Okay? And I will leave it there because next time we will start with, yeah, what do we do about it? Yeah. Yeah.
So I'm actually kind of confused about what is